All right, so need some more chalk here. Okay, so we definitely see a pattern here, right? So let's use that pattern to come up with a formula. Okay, so what we've observed so far is that anytime there's a joint connecting two rigid bodies, the number of parameters goes down. If it's a 1 degree of freedom joint, it goes down by 2. If it's a 2 degree of freedom joint, it goes down by 1. If it's a 3 degree of freedom joint, what do you think? Goes down by 0, stays the same. Okay. All right, so I'm going to give you a formula, and it's called Grubler's formula. Okay, and I want to remind you that this is the planar version. Okay, all right, so here's the formula. So n is the number of links okay, and it's also important to emphasize here that we're going to include ground. Okay, so the ground is also a link. Okay, I didn't make up the rule. That's how it's been, so that's what we're going to go with. Okay, so number of links includes ground. J is the number of joints. Okay, now we can have different types of joints. Okay, so let's say that F sub I is the degrees of freedom, DOF of joint I. Okay, so we have I from 1 through J. Okay. All right, so the formula then is, and let's go through the logic here. So if we have n links, and these links move independently, we need 3 coordinates for each link, right? So it's 3 times n. But remember, we're including ground in n. So let's eliminate ground. Okay, eliminate ground. Okay, as I said, I didn't make this up. That's how it's done. So n includes ground. So let's subtract ground. Okay, and now every time you see a 1 degree of freedom joint, the total degrees of freedom goes down by 2. For a 2 degree of freedom joint, the total degrees of freedom goes down by 1. Okay, so minus summation from I from 1 through j, 3 minus f sub I. Okay, so this seems like this formula captures, okay, the reasoning that we described earlier. Okay, all right, so we can actually make this a little bit simpler. Okay, so it's that. Okay, so here's our candidate formula that will allow us to calculate the degrees of freedom of a robot mechanism just by counting the links and joints. Okay. Okay, let's see if it works. Let's see. Well, the 4-bar linkage we already did, so let's do the 5-bar linkage. Okay, I'm going to add one more link in this structure. Okay, so let's now count the number of links. So we have 1, 2, 3, 4. Don't forget ground. So 5. Number of joints, 5. And the degrees of freedom of each joint, they're all R joints, so it's 1 degree of freedom. Okay, so it's 1 degree of freedom for all I. Okay, so now let's plug these numbers into our formula. So DOF equals 3 times n, 5, minus 1 minus j, 5, plus the sum of all the joint degrees of freedom. So we have 5 1 degree of freedom joints. So this is plus 5. Okay, so you can do the calculation. It's going to be 2 degrees of freedom. Okay, so if I fix values for 2 joints, any 2 joints, okay, that will determine, okay, the configuration of this mechanism. Okay, in other words, I can control 2 joints independently. Okay, so this seems to work. Okay, let's do another one. This is an example that I threw out to you in the first lecture. Okay, so there's a leg there, leg here. Let's make things a little bit, well, just change things just slightly. Okay, so I'm going to replace this structure with a P joint here. Okay. Okay, so it's a P joint. All right, let's calculate the degrees of freedom for this. Okay, number of links. So 1, 2, 3, 4, 5, 6, 7. So if there's a joint, remember a joint is something that connects 2 rigid bodies. So if you see a joint, there has to be 1 rigid body on this side, another rigid body on the other side. Okay, so 7. And then, don't forget, ground. So that's 8. Okay, number of joints. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the degrees of freedom, all 1 degree of freedom joints, so it's 1. Okay, so let's plug it in. Okay. So what is it? It's 3 times n minus 1 minus j plus total degrees of freedom. So 9 1 degree of freedom joints plus 9. So this equals 3. Okay, so 3 degrees of freedom. Okay, so that means I can control 3 joints independently. Okay. All right, so pretty straightforward, I think, right? So it's almost, it's a mechanical procedure, right? Count the joints, count the links, plug it in, and you're done. All right, so I don't want you to get bored, so somebody help me out with this one then. Okay, so what happens here? Number of links, 1, 2, 3, 4, 5, 6, 7, 8. Number of joints, 1, 2, 3, 4, 5, 6, 7, 8. Each joint is 1 degree of freedom. Throw this into our Grubler's formula. 3 times n minus 1 minus j plus 8 degrees of freedom. So this is 5 degrees of freedom. Wow, that seems an awful lot, right? So if I fix 5 joints, okay, that means this becomes a structure, it cannot move. So this is 5, whereas that's 3. Something doesn't seem right, right? Okay, something's not right here. Okay, this is wrong. This is wrong. Okay. Now, what you have to remember is that a joint is something that connects 2 bodies. 2 bodies, 2. Okay, not 3. 2. Okay, joint connects 2 bodies. So what's going on here, actually? I mean, the right way to. Okay, so if we blow up this part, okay, what's going on is we have a joint that way, and we also have another joint here, like that. Okay, these 2 joints happen to be overlapping. Okay, but you should think of these as 2 different joints. Okay, they just happen to be overlapping. Okay, so in fact, the DOF is still 3. Still 3. All right. Okay, so looks like Grubel's formula still okay. Okay, still we can believe it as long as we interpret the joints correctly. All right, let's do another one. So here's one. Let's see. Okay, so all right, let's get to work. Number of links: 1, 2, 3, 4. Ground: 5. Number of joints: 1, 2, 3, 4, 5, 6. Each degrees of freedom of the joint is 1. So calculate the degrees of freedom. 3 n minus 1 minus j, which is 6, plus 6 1 degree of freedom joints. So this is 3 times minus 2 minus 6 plus 6, 0. Okay, so question. That's 0. So 0 means it can't move, right? It's a structure. It can't move. What do you think? Do you think this can move or not? At least the way I drew it, it looks like it can move, right? Looks like it can move. So what went wrong here? Is Grubler's formula wrong, or did we do something incorrectly, counting the number of joints or links or degrees of freedom? Not clear, right? All right, well, what if I drew this instead? Okay, and I asked you, does this move? And you would say, of course this doesn't move. Okay, so this is in fact correct. But this, if the link lengths are all the same and these joints all line up, then it can move, right? All right, so this is kind of a special case, okay? It's kind of a special case. So Grubler's formula is mostly correct, but it's not to be completely trusted, okay? It's like, you know, you have friends like that, right? Okay, so this is Grubler's formula, okay? You have to sort of be careful, okay? Don't believe it completely. Okay, so here's a good example. All right.